All right, we are live. So today I have a special guest on, Kevin Sabo. He is an MIT graduate student studying aerospace, astronautics, and aeronautical engineering. He has interned at places such as SpaceX, Pratt Whitney, and he is now interning at the MIT Lincoln Labs. And he's just going to give you a brief summary of the type of work he's doing now, and then we'll get into the rest of the conversation.
All right. Hey guys, my name's Kevin. Much like Mike said, majoring in aeronautics and astronautics. Been at MIT for, this is my 7th year, got my bachelor's and master's here, so now I'm doing a PhD. Currently, a lot of my work focuses on hypersonic aerodynamics, which basically is the study of the fluid flows over basically aircraft that are traveling somewhere around Mach 5, which you could think of as like 3,500 miles an hour plus, and then all the associated effects with that. That's more or less what I do. I have a lot of other experience. Some of my previous specialties included a lot of aircraft propulsion, rocketries, worked at SpaceX, stuff like that. So kind of have a breadth of experience related to the aerospace field.
All right, so if you want, do you want to talk about any one of those companies that you've interned at? Just to
up to you, however you want to structure this. It's your interview, man.
Yeah. So what kind of work did you do at Pratt Whitney? Because I read a little bit about. Are they like do they focus on building engines or?
Yeah. So Pratt Whitney, there's basically 3 big engine companies out there in the aerospace industry that supply for largely commercial aircraft, stuff you'd actually fly at if you were to take a trip down to Florida or something, right? Mm-hmm. Pratt & Whitney, General Electric, and Rolls-Royce are the 3 big players in this industry, and their main focus, besides GE, General Electric, their main focuses are jet engine development and commercialization of those technologies. So what I worked on when I was at Pratt was essentially I was working in the compression systems aerodynamics. So I was literally making compressors. You have, these things that take thousands of horsepower and compress air to pressure ratios of order like 18. So if it goes in at 1 atmosphere of pressure, what you kind of feel now, it comes out at 18 times that. So, 14.7 PSI times 18. And you got to do that over X amount of stages in this thing, blah, blah, blah. And then, they have other groups there that focus on the backside, the hot section, as they call it, of the jet engine, the turbines, stuff like that to power it. You got nozzle groups, all that stuff. And the whole point is get an engine out, develop an engine, put it on an aircraft, work with the aircraft manufacturer, which would be like Boeing, Airbus, Bombardier, Embraer, you name it.
Now, how long would it usually take to develop an engine like that?
So, yeah, those programs are on the order of decades. Usually 10 to 15 years is the average. They definitely take their time with it and make sure that they're getting everything right.
So what would happen if new research comes out or new findings come out? Do they sometimes restructure the whole project, or do they try to incorporate that right into the engine they're building?
So jet engines are very notoriously complex pieces of machinery, and I mean that obviously, but because of just that alone, a lot of stuff is built off of what's called legacy data. So a lot of previous research they've done over the course of, Pratt & Whitney, they did the Wasp engine in World War II. So, they've been around for a long time. So all this information that they've got from when they first started making jet engines up until now, they use all that in very clever ways to help design the next generation of jet engines. The kind of academia that ties into it too. So if there's any breakthrough stuff, they'll try their best to incorporate it, but they also want to make sure that it's not super risky. That way, both they can manufacture it safely, but also this thing can last on the wing as long as possible and not cause any problems.
Okay, so it's kind of similar with collecting genomic data and genomic mapping.
That I'm actually not too sure. I need to ask Pranam on that one.
You guys want to see that video? I did another video with Pranam. He's also at MIT, but yeah. So what kind of work did you do at SpaceX? Was it similar to that, or?
It was. So at Pratt & Whitney, it was a lot of compressor stuff. So a lot of just air compression. At SpaceX, I was in the turbopump team and did a lot of liquid oxygen and kerosene, essentially. It's called Rocket Propellant 1, RP1, basically kerosene.
Mhm.
but did a lot of liquid pumping. And a pump, its function is the same as a compressor for air. It basically jacks the pressure up. And the whole point to do that is the higher your pressure, the more thrust you can get out of your rocket. So when I was at SpaceX, it was a lot of a little bit of impeller design, stuff like that. Some different approaches on how to do that, and then mitigating other potential issues that happen with turbopumps, like cavitation, rotor dynamics, all that type of stuff. I saw most of that. Exactly what I did. I need to keep that a little. There's some restrictions in play that I can't really talk about. Some of it,
Oh yeah,
but
that's okay. We were talking a little bit before this live stream started, and I didn't even bring this up. But how did you become interested in rocketry or in
so I guess I could go in the Wayback Machine. When I was in fifth grade, like we were out, having recess and whatnot, and then I heard this loud noise, and of course everybody hears it. And I'm from like Southern California, so I like northern part of Long Beach was where I went to school. So I was not like super close to the Long Beach airport, but close enough. But 10-year-old me hears a loud noise, look over in the direction of the noise, and see these two little basically dots flying around. And at the time, they were F-15s. What they were doing in Long Beach, I have no idea. But all I knew is it's like, when you see something you like, you don't know why, you just know that you like it. That's exactly what happened.
Yeah.
So I was like, I want to be a pilot, this and that, go in the Air Force, blah, blah, blah. I told my mom, super excited. Seventh grade rolls around. Obviously, I'm wearing glasses now, so that went out the window. Got glasses, really sad and upset about that. And then mom's like, no, like, come from a family of engineers. My grandfather's an engineer, all that stuff. So went to high school, kept my grades up, heard about MIT halfway through junior year, applied on a whim, somehow got in. Still really don't know how, but I'll take it. From there, came here, didn't really know exactly what I wanted to do, but knew I wanted to do aerospace, and then slowly found my way into the propulsion field and more into the fluid mechanics side of things, and realized that fluids is something I like to do, and here I am.
So when did you take your first physics class, or did you have to take a lot of physics classes before MIT, or?
Yeah, so MIT has certain pre-requirements for high schoolers in order to get in, and they take location to account too. There's some schools that you can't offer it, but if there's a kid there working as hard as they can to create every opportunity, they'll recognize it. But the general requirements are you need to have taken at least 1 year of physics, I think 1 year of chemistry, 1 year of bio, and then up through calculus AB or something around that. My first physics class I ever took was my junior year of high school, and then senior year I took a AP Physics C, and I took that by myself because they didn't even offer it, but I didn't want to just do nothing. And then, when you get to MIT, every undergraduate you meet that's from MIT has had to take physics, both the mechanics and the electromagnetism portions of it. So we go through a year of physics our freshman year. It's what we call General Institute requirement, or a GIR for short.
Yeah.
So even the economists that come out of here, they know physics, they know everything up through like multivariable calculus. Most of them even know more than that because the economics here is all math based. It's economics. If you're an athlete here, you don't major in economics because it's hard.
Yeah, a lot of your time is going to be spent doing math problems.
Oh, God, the amount of time I've spent doing homework here, I can't even tell you. I haven't had to pull an all-nighter, thank God, but
that's good.
Keeping my stuff in order, it's been a struggle. It's stressful. I know a lot of people that have pulled all-nighters. Fortunately for me, some of the problems I kind of saw it and I understood what I was doing. There's students here, they come here, they just smoke it, like make me just look like a chimp. And then there's other students here. You do kind of wonder how some of these guys might have gotten in, but I'm not going to name any names, but it's any other school. It's just everybody here is, a little bit smarter than the average, I guess. I don't know. But yeah, MIT, there's a lot of homework. I can't tell you the amount of hours because I lost count after a few thousand.
So you sent me a little bit about well, not a little bit, it was 174 pages of the thesis work that you did. So
Yeah.
how does that tie into the work that you did at SpaceX and Pratt and Whitney? Because you were focusing on like blood flow, fluid dynamics. Is that?
Yeah. So the direct tie-in, there's nothing directly tied into that, but well, the one thing that they both share in common, the work that I did there, and then the work I did in my thesis for my master's, which, disclaimer from me is I don't think it was a great thesis. I didn't do as good of a job as I could have done.
That
But
was your topic. That was your choice to do that topic.
Well, I had a tricky situation. My old advisor, he was difficult to work with. Definitely a great dude outside of work, but when the work environment came around, we just didn't see eye to eye on things, and he was very intense.
Mhm.
So I opted to switch out, and I talked to some folks, and they're like, "Yeah, don't worry about it. Like this happens all the time. Like sometimes you just student and advisor relationships don't work out. You're good." So this was one of the projects that was available, and my current advisor, he does this as well as hypersonic stuff. So it's a very fluid mechanics based problem. And that's where the link is. It's in the fluid mechanics. I've done fluid mechanics a lot, so switching over to that perspective, it wasn't the biggest leap. But as an aerospace engineer, trying to work on blood flows when your previous experience is in jet aircraft engines and rocket engines, it's quite a jump.
It seems like it would be. So how did you tie in computational fluid dynamics? Is that just basically the database that you mentioned earlier, or how does that tie into it?
No, so computational fluid dynamics, basically, there's a lot of physical modeling that we do in physics, and the governing equations, what we call governing equations, the math that basically we have set currently is the most accepted model for this stuff. These equations are referred to as the Navier-Stokes equations, plus other conservation laws. All this ties in together. And as long as you have a geometry, make some assumptions about what's going on in your flow field and everything, you wind up being able to simulate quite a lot of stuff. These equations, you cannot solve them by hand. There's actually, it's called the Millennium Problem out there. If somebody finds what's called a closed form solution, or basically you can handwrite out a solution to this thing, they win $1 million.
Wow.
And the researchers, they don't care about giving away the million. If you could find a closed form solution to this, this is incredible. Like, I think his name's Terrence Tao, if I remember correctly. Don't quote me on that, but he's one of the math prodigies over at UCLA. He's working on this problem, and even he's struggling with it. And this dude's made so many breakthroughs, it's unreal. So these problems are very difficult to solve. But you can actually, fortunately, discretize these into a digital domain, or just discrete chunks, and simulate it all on a computer. So what I did was just that, put it on a computer and then simulated the problem out. And then you can basically set up your model to where you can put blood cells in it and model what happens when they sickle and sickle cell anemia based on oxygen stuff or concentrations, which have their own set of equations they follow. And you iterate to a solution over time and check the results and see what's going on. And then with reasonable confidence, you can actually experimentally verify this, or if this stuff's kind of standard and very well accepted already, you can say, this is the predictive capability we got. This is our prediction. Here's how we go from there in terms of treatment options, stuff like that. Like, what do we need to monitor to help treat people that go into what's called crises? Oxygen gets low, sickle cells start clogging the capillaries. What do we do to unsickle it or prevent the sickling from even occurring in the first place? Is it even possible to reverse the sickling once it's occurred? How do we do that? Do we do it by drugs, oxygen pressure treatment, all this different type of stuff? But yeah, so that's mainly how the CFD tied in, just identifying those little factors, what knobs to turn to help prevent this from occurring.
Now, this is sickle cell anemia? I mean, it is a genetic issue, right? Like it's
yeah. So yeah, you're getting back towards the CRISPR stuff. I could feel it. And I'm a little bitter about CRISPR, even though I recognize CRISPR is an insanely powerful tool. I'm all for it succeeding. Do not get me wrong on that. But
it's cutting corners or something.
No, it's not cutting any corners. It's just a lot of my research. Once we found out they were doing studies with CRISPR on mice with sickle cell anemia, they managed to actually use CRISPR successfully to edit those genes out and cure them from it.
Right.
So, my research, I'm sitting there like it's useful in the short term, but long term, it's, once CRISPR hits the shelf, essentially.
Yeah.
Yeah. Sickle cell anemia is no longer a problem.
Right. I was going to ask, I was reading in the thesis that you sent me is that that doctors are using this to kind of formulate treatments for patients with sickle cell anemia. But I was going to ask if CRISPR gets to that point where they can use it in humans to just change the base.
Yeah, that research goes out the window.
Yeah.
It becomes more of an academic curiosity, which it's fine to do that. That could inspire somebody to treat, a different problem that maybe CRISPR can't tackle in a similar light the way I did it. And, that's totally fine. So it's not totally worthless, but at the same time, my treatment option is not going to be standard by any means.
Yeah, I was even reading that there are African cultures that are actually born with sickle cell anemia as like a defense mechanism.
Yeah, it helps against malaria.
Right.
So the only problem is you go through, sickle cell crises, stuff like that. So your life expectancy drops to like, late 30s, early 40s, as opposed to a full healthy life. But yeah, it definitely helps against malaria. And that's the reason actually sickle cell anemia in some African cultures has propagated so much, because malaria just can wipe so many people out. If you have something that helps you survive, even if it doesn't help you survive the full life expectancy of what you would consider for an average human being, you're still surviving and being able to reproduce. So it's kind of...
Because with malaria, is it more of an instant death or?
I actually don't know, but I definitely know if you get it, I think you can survive, but given the conditions out in certain parts of Africa, not first world, unfortunately. So they have to struggle with it a little bit more than we would. We just go to a hospital. They'd know how to at least treat it and sustain it to where we can make a full recovery. But some parts of the world, unfortunately, that luxury is not an option.
So, I mean, maybe a culture like that would benefit more from a more conventional treatment than CRISPR. They have access.
It depends, because if it's drugs that do it, then potentially. If it's very high tech machinery, then well, can they afford to even get access to? That's the question. And with Pranam, I know like what research he's doing. I've seen where he works. The Media Lab, they're about connecting humans to technology as in like the most ready way possible. Can they interface humanity with technology and make it very easy to do so? So, the end goal is, right now, the first step is, work the bugs out of CRISPR. Next step is, okay, after we do that, commercialize it, get it going. And then step after that would be, okay, now it's commercialized. Can we make this, cheap to do and really readily accessible to everyone? Once money gets involved, though, that could be difficult, and that's a different topic entirely. But at a high level, that's essentially what's going on at the moment.
And then there's probably going to be a big ethical debate on whether we should even use it.
Yeah. Yeah, I've heard CRISPR likened to you're essentially able to play God to some degree. Like a lot of people are like afraid of like, okay, like can we with CRISPR edit genes and cosmetically alter our babies or genetically make them like superhumans? And while that is a legitimate concern, it like hypothetically it could happen. But the unfortunate reality is the human genome, the code we got for it in terms of the actual genetic code, it's so ridiculously complex. It's probably not even going to be possible within my lifetime. I'm not at all current on the research, but from the researchers I've talked to, they're focused on very specific instances, identifying a gene, editing that. I can't tell you why my eyes are blue exactly. I can't tell you why I wound up being 5'8". Some people, they want to have like, oh, I want my kid to be 6'8" NBA player. I'm just sitting here like, well, that's great, but I don't think CRISPR can do that for you right now. That's not the main focus.
Yeah, 'cause I mean, even if CRISPR, or even if we can use CRISPR to cure some diseases, it's like who knows if new diseases are going to arise after that we can't even deal with because we made some genetic modification, or if we're going to need some new technology to go beyond genes because we don't know what's beyond that. Just
Yeah, that I'm not fully. I'm definitely not up to date with that, but I know for like bacterial stuff, viral stuff, it's bacterial. It can be more toxicity based, bacterial byproducts from metabolism and stuff. Viral stuff, they go in and the virus will basically take control of your cell, edit its genome, essentially reproduce, blah blah blah. So they're actually thinking now, like this is actually a really cool tangent shot. Um, so like a lot of antibiotics, right? There's penicillin, for instance. It blocks a lot of the stuff that bacterial cells have to do to function, and then it kills them.
Mhm.
Now, some bacteria, there's resistance created when that happens, and the strongest survive. They go on to reproduce, blah blah blah. Similar to like sickle cell anemia in Africa, the strong ones survive. Bad, a bad thing's happening that they have sickle cell, but malaria can't do anything to them, so they survive. With the viral stuff, though, because they're like the way they attack cells and cause disease, they edit the genomes of the cells and actually go in, take over basically the control faculties of the cell, reproduce itself crazily,
Mhm.
kill the cell, and then spread and process, repeats itself ad infinitum until your body can take care of it. Engineers now are looking at, okay, what if we took that mechanism of a virus that can actually go in and edit a cell? Instead of using like antibiotics, what if we use this virus to target bad cells? It goes in, edits the bad cell, the disease is, if it's a bacterial based disease, and it just kills that cell. It doesn't kill healthy cells. It's like a guided missile just
Yeah.
hitting only the bad cells. So like there's a lot of like interesting medicine out there beyond CRISPR that's being studied, and there's a lot of potential opportunity for it to actually really cure a lot of stuff. Like the viral one, that's a huge potential answer, I should say, to the antibiotic resistance problem that the world's facing right now.
Right.
Now, are people going to be okay with injecting phages into you as a treatment? There's a PR thing with that, so that's a little difficult. But I think there's been a few experimental studies where it's just like, okay, like this guy like is dying. There's no way he's going to survive. He needs to do this in order to have a chance.
Mhm.
It worked. So there's hope. There's promise out there. A lot of these big problems that are getting sensationalized now, like the antibiotic resistance problem, all these genetic diseases and stuff, like engineers are definitely working on it, figuring out ways to get rid of it and deal with those problems and actually really make things efficient. So
Yeah, it seems like with the with viruses that we might have more of an idea of how that mechanism works. So that might come even before CRISPR is used regularly. So
um I mean, anything could happen. I don't know for sure. Like, this is definitely not my field of research. A lot of the stuff I remember just from taking biology here because I was required to. Uh, I think a lot of it could be a function of money. How much money is being thrown at it will definitely influence how effective it'll be in the future. But if a breakthrough is made, breakthroughs can happen anytime. Inspiration can hit somebody, and then all of a sudden, wham, we understand everything, or everything about that particular problem. That could usher in a new era almost immediately. So there's a lot of factors. It depends. It definitely, either option though is a good option. So at this point, you know, if one succeeds, it's not the end of the other one. They're both very useful for certain things.
both going to keep progressing in their own direction.
Oh yeah, there's no doubt in my mind that both of these things will be understood pretty well within the coming years. So
Yeah. So we want to move on from the CRISPR side of things.
yeah, sure, no problem.
You want to talk about what you're doing at the Lincoln Labs there? We kind of discussed a little bit, but if you just kind of want to.
Sure, I could talk a little bit about it. Some of the stuff I can't actually say too much for obvious reasons, but I guess just kind of more of the advertisements thing of what Lincoln Labs actually does. Lincoln Labs with MIT, they're very much intimately partnered, and they're they operate in the interest of national defense, do a lot of research and stuff, similar to, like, you could think about if you've heard of like Sandia National Labs, all those types of things. Their main focus is on sensing technologies. So as we were talking about a little bit earlier, like if we can see something in the sky, is there a way we can, like, how are we seeing it? How do we sense it? How do we, identify it as, consistently across the span? Are there ways to not see it? And if there's ways to not see it, what are those ways? How can we get around those? Like the whole point is like, that's one instance. That's like radar, LADAR, stuff like that, or LIDAR. Sorry. Basically their whole thing is sensing stuff. It's all sensor technology, stuff like that. Not like censorship, but like sensor with the S. So I gotta be careful when I say that. Some people take it the wrong way. But yeah, so yeah.
I would say so. You were talking about how it's mainly for, or a lot of the research there is for defense purposes, like being able to detect missiles and things like that.
Yeah. Some of the work I do is largely in they brought me in because I do hypersonic aerodynamics. Yeah, we work with the missile teams there, a lot of sensing stuff like that. So
now, I was reading on their website a little bit that they do stuff with space mapping and quantum and other stuff like that. What is space mapping exactly? Like, are they doing work there to actually try to create some kind of map of space as far as we know, or?
Okay, so aerospace is a huge field, and that is definitely not my area of expertise. I would imagine, just by the way it sounds, that yeah, it's probably literally stuff to map out space or map out stuff in space, be it there's potentially stuff there for satellites, tracking satellites, identifying space junk and debris so you could safely launch stuff. It could even be stuff for telescopes, identifying quasars, building a map of, like, basically these quasars can act as like lighthouses and stuff for spaceships in the future, and kind of give you not a GPS, because GPS is for globes, which is Earth, but like a more universal positioning system based on stuff like that. So yeah, those are the types of problems they look at: sensing and identification of different things and understanding where it is to help, be it a DoD source, military machine, or even a commercial source that wants the research done and they pay for it, helping them accomplish their objective through sensor technology.
Okay. So, and before we went on, you were talking about how they're using, or how they're trying to detect ions in maybe the fumes of some of these aircraft, or.
So a lot of my PhD research revolves around that. I came up with the topic on my own. Just, I told you before, I was under fellowship. My advisor's like, research whatever you want in the field of hypersonics. So it's like, oh, cool, crap, wait a minute, there's a lot out there. So, it's a blessing and a curse. But I wound up on that topic because a lot of the chemistry and everything, that type of a problem was interesting. It interplayed with the fluid mechanics. It's a very multidisciplinary problem, and that kind of attracted me to it. There's always a lot to learn. So, I'm a nerd, obviously, so I was all for it. So when I went to Lincoln Labs, they have a lot of tools and stuff that we can use to help simulate these things and really get some good research done. And MIT doesn't have those tools directly, but because we work with Lincoln Lab, we'll hopefully get some access to it to use for our research purposes. Anyway, that background aside, yeah, Lincoln Lab right now, they are looking at that type of a problem. It has to deal with sensing it. It's very interesting nonetheless. I can't talk too much more about certain parts of that problem, but yeah, so what's out in the general literature, which anybody can access through Google, though, what I can say is we're currently looking, I know the U.S. Air Force, they published this back in March of this year. We're looking at figuring out ways to identify those wakes. Radars can sense when there's free electrons or free ions in there. Anything with a charge that's not neutral, the radar can see it. So we're trying to figure out and understand, how are these charges produced? Understanding, okay, we know that, like, it happens because these things are going so fast through the atmosphere, the air is ripping itself apart. Temperatures, like I said, they're order 2,000 to 4,000 Celsius in certain parts of the flow field. So the air wants to ionize depending on how fast you're going. these things will be seen. So they
Now,
want
ionizing just meaning spread into smaller particles.
no. Well, yes and no. That can happen. Ionization directly, I guess, in the simplest definition of it, is basically you're just taking electrons off of some molecule. Um, so there's multiple different reactions. There's a lot of technical terms, but like when you go from like oxygen, like O2, which is what exists in the atmosphere, it's very stable. If you pump enough energy in, the two oxygens will rip apart and just oxygen and oxygen, just O and O. That's called a dissociation reaction. That's actually not ionization, but as you start putting more chemicals in and there's a lot more stuff going on, the energy doesn't necessarily distribute itself equally in the flow field. These are what are referred to as non-equilibrium flow fields. The energy is very confined to certain chemical species because there's certain amounts of time it takes to actually have these reactions occur. At that point, these oxygen molecules, they can interact with other, molecules in the air. You could have multi-body collisions and electrons will fall off, and there's a lot of stuff going on. So yeah, there's ionization. That's one product that actually occurs in these types of flow fields, but there's a whole bunch of different stuff going on. We're trying to figure out and understand how all this stuff occurs, why it occurs, what happens when you have different scenarios in the flow field, and really relate it back to, can we look at the wake and make a good guess as to what caused that wake, and then identify what would be considered a target, I guess, if you will. And like everybody around the world's working on that. It's an interesting problem, and it's in the interest of national defense for countries everywhere.
That was actually the next question. What other countries are focusing on this?
Largely China and Russia, the geopolitical foes from the Cold War. It is what it is. I mean, China right now is building I think a Mach 40 wind tunnel, which is more for re-entry type speeds. I mean, it's incredibly fast. So that's been out in the news lately. Russia, I think Putin came out and said something about having a hypersonic missile that was like able to travel, under radar or something. It was stealthy. Like you could actually have it go very near sea level at like Mach whatever. And I did a back of the hand calculation on that. Everybody's freaking out about it, but I don't want to say anything too negative, but he doesn't know what he's talking about because there's no material on Earth that could withstand that type of heat loading. It would vaporize in nearly an instant. So, I don't know. There's a lot of countries working on different things. A lot of the stuff right now is kind of hot air threats. At least from my understanding, I could be completely naive. So, like, I don't have clearance. I don't know anything. If I did, I wouldn't say it, but you get the point.
Yeah. So the main application for defense and for launching missiles and things like that.
Oh, I didn't get the first part. Sorry.
Oh, so the main application of actually understanding these ions and detecting them would it be more to actually detect missiles or to send them in different ways than we can now?
A mix of both. So obviously, to Lincoln Labs, they're sensing, they want to detect. Clearly, that's the obvious case. There's also some interest in commercial hypersonics, being able to, travel from London to Sydney in 4 hours would be great.
That would be.
Yeah. So right now it's, I think, conventionally like 18 or so hours, roughly, 17 to 18, somewhere on that order. So being able to get there in 4, the world shrinks even more. And it's awesome. But, a few years ago, MH370 happens where, flight crashes in Southeast Asia. Nobody knows what the heck happened. They can't even find it. So what if, I pitched this to my advisor. I said, what if commercial hypersonics becomes available, but the standard way to detect things, you got a bunch of ions in there, radio waves, stuff like that. It might not be able to penetrate that cloud depending on what's going on. We might not be able to detect that stuff and communicate properly. If we understand the mechanisms that's going on, we can potentially generate even more ions in these flow fields and actually have radar that can actually just see the aircraft going. So you can keep track of it just by the fact that it's flying, as opposed to having electronic equipment that does it for you. And this is obviously not the preferred method. You want to be in constant communication, of course, but stuff like that, it's a nice safeguard to have. No matter what happens, you can see what it's doing. You can prepare for it. If something goes wrong, where it was last seen, and you could get a good idea of what's going on.
Do you think that's probably one of the biggest barriers moving forward with like hypersonic vehicles would be the safety aspect of it and being able to actually keep track of it over a long distance like that?
No, not even close. I like spinning it that way because it gives me money for my research. But it is something that needs to be understood, of course. I'm not downplaying that at all. But the biggest barrier for hypersonic stuff is the energy costs. These things require so much energy to sustain flight at that type of speed. It's unreal.
Would solar not even be enough for that?
Oh, solar's not even enough to fly like big aircraft at like 200 miles an hour. Solar wouldn't even come close. The energy requirements for this thing is probably like 4 or 5 orders of magnitude higher. It's insane how powerful these things are, or how much power you need for these.
Would you need something like a superconductor to run even like one track, or how would you even know right now how they would even produce that much energy?
So
for content.
So in-flight stuff, we would use what's called a ramjet or a scramjet. A ramjet, basically, a jet engine, what it does, the way I remember it, it's really easy to remember, and you'll hear why if you have a gutter mind like I do. The way we were taught it is a jet engine works by sucking, squeezing, banging, and blowing. Sucks air in, compresses it or squeezes it, bang, combustion occurs, and then blows it out the tailpipe over a turbine and nozzle, generates thrust. A ramjet, the squeeze part of that actually just occurs from the fact that the aircraft's flying extremely fast through the atmosphere. So the air has to slow down. When it slows down, it'll compress itself because that energy has to go somewhere. So it goes in it stores itself in the form of energy per unit volume, which is pressure. You could also think of pressure as force per unit area. A fluid mechanics person like me, I think of it as energy per unit volume. It's a very potential energy type thing. With that, you can basically pass it into the combustor, combust it right then and there, and then accelerate it out of nozzle. So the SR-71, for instance, the spy plane of the Cold War that we had, Mach 3 plus thing, see it on the History Channel all the time. That actually used a ramjet when it actually hit cruise speed. So that engine is immaculate as far as I'm concerned. But you could look it up and see that stuff. It's very much open source at this point. The fact that worked was fine. It's flying at like Mach 3, but the hypersonic stuff we're looking at, we're trying to fly at like speeds of Mach 6 to Mach 8. So the engines here are totally different.
So do you know if you know what work is being done to deal with like the heat and the pressure going at hypersonic speeds?
So yeah, I know it relates to this, but like, okay, so let's just start from like the first one. The heat loading. Heat loading is definitely the hardest part when you're flying in the atmosphere. You're ramming into air. It's really freaking hot when you hit it. Like the Blackbird, I think, had a fuel flow system on its skin to cool it effectively. I think the Concorde might have even had some pumping stuff just to keep it balanced properly. And that was flying at like Mach 2. That even had some issues. But anyway, the heat management, or what we call like thermal protection systems, if you're flying really hot, this thing wants to melt. So you have to keep it from melting. Otherwise, you don't have a plane. And obviously, that's bad. At that point, that I think is the biggest issue. The pressure, stuff like that. We're not dealing with insane pressures to the point where we'd have to worry about stuff exploding or not exploding. Exploding is like combustion stuff. There's a technical term for it, but basically it just pops. We don't really have to worry about that. But how to efficiently pressurize and not waste any of that energy from the air coming in because we're flying through it so fast. That conversion process, how efficiently we do that, that's a big area of research. But yeah, The largest part is managing the heat so that nothing melts and we can sustain flight for long periods of time.
Now, do you know of any, are there certain metals that they're looking into that would sustain that heat, or is it
Um,
wrapping?
well, there's stuff that does work for sure that sustains the heat really well. It's just straight up pure carbon, like graphite type compounds. Most metals will actually melt. So at the temperatures we're talking about, if there's any actual metal that would do it, I don't actually know. I would imagine they would be very much classified. They'd be at least proprietary information, if not even classified, because if you get these metals, it turns into a national defense issue. But yeah, I don't know if there's any actual metallic stuff out there. I'd be surprised if there was, but there could be. I don't know.
Okay, well, I think I basically covered everything I wanted to bring up. I'll post a summary of this to my Instagram, and I'll write one on Facebook too, and also add some stuff in the description. But yeah, this was a really interesting conversation. So thank you for taking the time to do this.
Yeah, no problem, no problem. I'm on internship, so I don't have homework, so I have a little bit more time now.
Okay, yeah, maybe we can do another one of these in the future if you'd want to.
Sure. Yeah. That depends largely on whether or not I can talk about my work.
Right.
So I don't know if I don't know. It could happen for sure, though. I'd be down to definitely do another one.
Okay, cool. Thank you.
Yeah, no problem.
All right, see you later, Kevin.
Yep. Catch you later.